Welcome to the lecture videos for Lecture 4 of Privacy in Machine Learning and Statistics. I'm Adam Smith. So for the last couple of lectures, we've been looking at reconstruction attacks, which in some sense tell us what we shouldn't publish. Right? They show how we can take a relatively large collection of relatively accurate statistics and use them to kind of infer a pretty accurate picture of the original data set. Now we want to turn our attention to more positive statements. We want to be able to, assert that something we want to publish won't allow for these or any other kinds of attacks. And for that, we're really going to have to try to spend some time nailing down what it is we're trying to prove about these algorithms. Like, what does it mean to, to state that a thing we want to publish doesn't violate privacy? Okay, so this is not a new question. It's been looked at since the 1960s. There are broadly two approaches, very broadly two approaches people have taken. One is to just a sort of an ad hoc approach where you formulate a specific set of attacks. And you look at algorithms or mechanisms for publishing stuff that resist those particular attacks. Okay, so a classic example of that is what's called k-anonymity that I'll talk about. There are a bunch of others. The second approach, which is the one we're going to prefer in the class mostly, is to formulate sort of general criteria for what it means to protect privacy and prove that algorithms that satisfy these criteria somehow resist all the attacks we would want to prevent. And then also try to design algorithms that satisfy these criteria. So that's where we really want to go with the class. But before we get there, it helps to kind of see what goes on a little bit with this first approach. Okay, so a good example is k-anonymity. This is a notion. It's a notion of like what you can do to make linkage attacks specifically harder. So it applies to specific kinds of data. So we're going to think of our input as a table of records. Each record has a bunch of attributes. And the output is a table of exactly the same dimensions in which entries, some of the entries are left alone. They're there, as they were. And some of them have been what's called generalized. So when you generalize an entry, what that means is you take a specific value that was in like one of the cells of the table, and you replace it with some description of a subset to which that element belongs. So for example, you could take the number 2 and replace it with the interval like 1 to 3, right? You could say this value, I'm not going to tell you exactly what this value is, but it's between 1 and 3, right? Or you could take male and replace it with the, the pair male and female, meaning it's either male or female. You could take, the name Adam and replace it with a special description saying this is a string that starts with A. There are lots of other types of generalization that are possible, but this gives you the right idea, I think. Okay, so when we look at, to make a table k-anonymous, what we're doing is we're trying to generalize some of the entries roughly so that after this generalization step, every row is identical to at least k-1 other rows. Or another way of saying that is that we group the rows into sets of size at least k, and we generalize them so that within these sets, the rows end up looking the same. Okay. It's a little more complicated than that. So in fact, what the idea of k-anonymity is to partition the attributes into non-sensitive and sensitive attributes. So non-sensitive ones are the ones that are assumed to be present in other data sets to which the attacker might have access. So these are things that might be used for a linkage attack. Okay, so these are the things that are generalized, and so the criterion is that if I look just at the non-sensitive attributes of the rows, then every row after generalization should be equal to k-1. Its non-sensitive attributes should be equal to the non-sensitive attributes of k-1 or more other rows. Okay, whereas the sensitive variables are just left alone. So essentially what we're saying is like, there's a set of records that fit this template, and here is the set of sensitive variables that goes with those records. So, k-anonymity was designed to make it harder to carry out linkage attacks, and indeed, it seems that it probably does that. Given a k-anonymous table, it's hard to identify any record uniquely, especially if you only have access to other sources that are about the non-sensitive attributes. And so it seems it's hard to link these things to other information sources and sort of understand whom you're drawing inferences about. That said, there are lots of problems that k-anonymity kind of allows that aren't captured by this idea of a straightforward linkage attack. Okay, so what kinds of things can go wrong? Well, I can learn that, for example, everybody in a group has the same sensitive attribute, right? Everybody in this group has their sensitive attribute is the same. So if I know that you fit this template, then it doesn't really matter that I don't know whether you're row 9, 10, 11, or 12. I still learn your sensitive attribute. Okay, and also this format like allows me to rule out certain values. If I know Alice is in the table, I know her sensitive attribute is not broken link. There are lots of other things that can go wrong, and the point is that when you design something specifically to resist one kind of attack, you're really opening yourself up for other kinds of problems. Okay. So like one kind of thing that goes wrong with k-anonymity that is going to be sort of instructive for us when we think about differential privacy are composition attacks. So what do I mean by that? Suppose we've got two data tables whose rows overlap. So there are rows that appear in both tables. Okay. And now suppose that these two tables are anonymized independently, like say they're managed by separate health clinics or something like that. If I know some particular person's record appears in both of these tables, and I know a little bit about that person, then I can learn quite a lot of information, right? So for example, suppose I know that Alice is 28 years old and lives in zip code 13012. What I know, I suppose I know that her record is in both data sets. Well, I can see right away that she belongs to this first group of people in the first table, and this second group of people in the second table. And if I just compare the sensitive attributes, I see that their values, there's only one value that appears in both of these sets. Okay, so this is an example of a notion of an approach to anonymization that's very brittle when we start composing simple algorithms to build more complex systems. And as an exercise, you can ask yourself, well, suppose I know that somebody is 58 years old. Well, what can I infer about them from these two data sets? Like, how much can I narrow down their value of the sensitive attribute? Okay, so the last point I want to make about this approach is that it really highlights another important point, which is the difference between focusing on the form of the output versus the information content when we're trying to define what it means to preserve privacy or something like that. Okay, so one of the things that's going on with k-anonymity that's a problem is that it just specifies a set of acceptable outputs. It doesn't really restrict the process or the algorithm that produces the output. It does a little bit in the sense that you have to use generalization, but it doesn't tell you how you select which things to generalize. You in fact have a lot of leeway for that. And so, for example, this leads to more opportunities for leakage. So for example, if I know that an algorithm uses like the narrowest possible interval for each set of values it's given, once it's decided to group K records together, it generalizes to the narrowest interval it can. Then for example, I would know that there's in this group, there's a 30, someone with age 30, and someone with age 39. One of these is a 30 and one of these is 39. I don't know which is which, but that already gives me a certain kind of information. And there are examples of more sophisticated things you can figure out. The upshot of this is that if we want meaningful definitions of privacy, and certainly like general purpose definition, it's not enough to look at like the form of the thing that our algorithm is producing. We actually have to somehow understand the process itself. We really have to focus on the algorithms themselves. Okay? And so what we're now going to do is turn to a definition, really a family of definitions that do exactly that in the next video.